Okay, so the last thing I talked about in the first video was dynamic matrices, and I mentioned how you can use pointers to pointers, a pointer to an array of pointers. This is the old, what we might call the old school approach, and there's some danger and tedium with using this approach because of the use of the new operator. If you don't want to permit memory leaks, you have to use the delete operator, and using the delete operator with pointers to pointers can be especially tedious, in my opinion. So nowadays, in modern C++, after C++ version 2011 was standardized back in 2011, they usually call it C++11. Um, the vector became included by default. Whenever you install a C++ compiler, you get the vector header file by default. So a vector of vectors, an array of arrays, a dynamic array of dynamic arrays. So we can, using something like this, we are still restricted to the data structure is homogeneous. This dynamic array can't consist of mixed elements. But we could put in a class object here, of course, our own class object, like a vector of cars, like a parking lot of cars. So this is powerful stuff, potentially. You can make a vector of vectors, a three-dimensional array, which you might think of as like a parking garage. There are a certain number of rows and columns in a certain level of a parking garage, and there are multiple levels of a parking garage. Just to give it some a concrete example, literally a concrete example, since parking garages are often composed out of concrete and steel. Okay, so talked about that last time. It's one other use of pointers is returning multiple. It's one way of returning multiple values from an array. It's not the approach that I would generally use. I would return a vector. Uh, some input here. So we can create a vector as long as we pound include it. This is a this is a way of returning multiple values that's more modern. So we can use the auto keyword, automatic type deduction. And in this case, I didn't use this. Well, maybe we push back some input. We push back the value 6. This is just a silly example that I'm getting into. So this return vector function returns multiple values. There are some complexities to it, but we've seen previously if we set a return type as an int, can we write a function called return multiple integers and return not just 4, but 3 and 2 and 1. We'll just generate a compiler error. Let's do this before we get into my returning a vector. So what will this print? We'll print 4, comma 3, comma 2, comma 1. It returns 1. So as you can see, or what seems to have happened is that these values just got ignored, and we might as well have just typed return 1. Is there some way, what if we say return 4 and return 1 and return 6? What gets returned here? It's the earliest return value, 4, that gets returned. Can we return an array? Can we say in a C style array of 5 elements? Does this work? Return array? It seems not. Expected a semicolon. Oh, excuse me. Okay, does this work? Return value does not match function type. So can we say an integer array of 5 elements? What does this say? Expected a semicolon. We can't return. It doesn't seem like this is going to work. So this is a modern approach for returning multiple values, multiple integers in that case. Returning an object of a class. This object's name is SumNums. So just to demonstrate that that works, let me go back to the code that I typed up previously. Auto result automatic. Auto means automatic type deduction. So if you say auto I equal 5 and you hover on I, you see that it displays int. So now in contrast, if I put a 5.0 f, I is a float. If I remove the f, I is a double. If I say auto I equal some words, the type of I is a const char, a pointer to a character array. Character array consisting of 11 characters. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's the string termination character that's invisible there. I think it's called the string, the character array termination character. Okay, so that's just a bit of detail on what auto is doing. So auto result, you can see the automatic. This is just convenient to use. We could say standard vector of int. It's not just convenient to use, but this works. If somebody else wrote the function return vector and we don't care, we for some reason don't want to type as much, or we don't care to spend the time worrying about what the return type is, we can use auto. It's commonly used. There are some drawbacks to it, probably. We almost certainly pay for the convenience of being able to do this. Okay, so this auto in this case is an integer, as you can see. Integers displayed there. Result is a vector of integers. A dynamic array is all a vector is in C++, and we print the num. So 1, 2, 3, 4, and in this function, which is not an incredible function by any means, we push back some input, whatever we take here. So 6. So we should see 1, 2, 3, 4, 6. And I also realize I haven't talked about the meaning of pushback. Pushback, is it pushing to the back? Or is it pushing from the back? So are we going to see 1, 2, 3, 4, and when we push back 6, are we going to see 1, 2, 3, 4, 6, or are we going to see 6, 1, 2, 3, 4? That's a reasonable thing to wonder. The function name pushback is not necessarily crystal clear in its meaning. It's more terse, it's brief, but let's just see how it works. This is a way of returning multiple values from a function. So we print 1, 2, 3, 4, 6. So evidently it is this first approach. Push back, pushes the element in at the back. Okay. So this is what we saw. So push from back, I suppose, is how I would interpret this function for dynamic arrays. And just to linger on dynamic arrays or vectors a little bit, we could say cout sum nums dot size. So size is the current size. The number of elements. Size before pushing input additional value back into the dynamic array, just to make that very long-winded. And then we could say cout size after is sum nums dot size. So the size before is 4 and the size after is 5. So the size of the vector is changed. There is something called capacity as well. So if we say sum nums dot capacity is not necessarily updated. This capacity right now might be 8, and it stays at 8 until we push back 8 until we've got 8 elements total, and then it increases to 16. We're not digging into the details of how vector allocates memory dynamically, but it makes some sense. Okay, so that is a modern way. This is a modern way. Excuse me. This is what I would use nowadays to return multiple values from a function, but you can also use pointers. And I think people who write in C exclusively would have to use pointers because C doesn't have classes. So they could return structs, actually, struct objects, because structs are supported in C. Well, let's not get into the weeds too much. Generate 1 through 5. I say int star first 5 ints equal new int. So this makes space for 5 integers in the heap in memory. This thing called the heap. This will not work in this case. So let's just delete it. Using our static array wouldn't be working in this case. I can't remember the details of what I was talking about here when I made these slides. Okay, return first 5 ints. So a pointer to the first, a pointer containing the address of the first element here. So generate 1 through 5 uses a for loop, and we use the subscript operator. So this suggests this relationship between arrays and between C-style arrays, static arrays, and pointers. Some have said that a pointer is a C-style array in disguise. So let's go to the main function and see how this works. We declare a pointer to an int in main, and we set this pointer to an int equal to the return value of the function. This is another way to do something similar to what I did with the return vector function, except this way saves a little bit, potentially saves a little bit of space, memory space. This use of a vector consists of some overhead. If you print the size of, if you say cout size of the vector object sum nums, and you compare that, I think you're and you compare that size to, so size of is not the same as the size function. size of returns the number of bytes that are occupied by some variable. If you print the size of some nums, this vector object, then you'll see that it's larger than the size of this this array of elements. If you take the size of, if you add up all the, this is this element here is going to be 4 bytes here. You will, if you add 5 here as well, it would not be, the size of some nums would not be 20. It would be greater than 20. Okay, for reasons that I'll avoid going into at the moment. Okay, so we generate 1 through 5. Notice that the data type is correct. If I change this to a pointer, there's an error that we've seen before. Now, if we use a loop, we say for int I equal 0, I less than 5, I plus plus. We enter an int at index I. This is an alternative notation to what I do in the slides here. So here I use the dereferencing operator and I increment pointer to an int every loop iteration, but you can also use this. So let's see that. And we generated 1 through 5, so they are 0 through 4, so not a very interesting output, of course. You see, I set it equal to 0, and I started at 0 and ran up until less than 5. Okay, but this is returning multiple values from a function. Okay, so didn't mean to spend that long on that topic, but as usual, I got interested in what I was talking about. So that's kind of the end of the introduction to pointers. Now, I've mentioned this before, the node class. Nodes are used. Nodes are, we probably have an intuitive understanding of what a node is. Just a colloquial definition of the word node. A point at which lines or pathways intersect, a central or connecting point like these. It usually makes us think of these pictures. We think of a node on a network. Nodes exist in plants. Nodes exist in the anatomy. Orbital nodes are a thing in chemistry. So this is, let me not get into that, but it's quite an interesting thing. Yeah, I think nodes are pretty, not the easiest thing to define necessarily, but we have a hand-wavy understanding of what it means to be a node. But they are used in graphs, trees. This is a tree data structure. This is the root, and these are leaf nodes, and these are intermediate nodes. This node here is a child of this root node. And so they're used in the tree data structure, which among other things can be used to represent file hierarchies on computers in storage and computer memory. And there's a thing called a graph data structure that uses nodes as well. So these are very useful with respect to many applications, but among one is computer networks, trying to find the fastest way that you can send data from Alice over here to Bob over here, for instance, to use the cryptography names Alice, Bob, Darth, Eve. Okay, but yes, we will be using pointers when we write a class called a node class, which is the building block of linked lists, trees, graphs. So that's some motivation. And we are going to write some classes here in a bit that consist of member variables that are pointers, not pointers to themselves. As in this case, that's called a self-referential data structure. But yeah, we'll see with the copy something called the copy constructor. If you have a pointer member variable in a class, there's something called shallow copy and deep copy, and this is a good thing to be aware of, because sometimes pointers can be nice to use. Okay, so suppose that we have this class called person, and they have a first name and a last name. So let's just define that outside of main here, and let me collapse these other things so I don't get distracted by them. So a person class, very straightforward, was one of our first examples. And we can say person, me. There's no construct, I haven't written a constructor right now. So we can do this. Now, if you come from Java, you may be familiar with the use of person equal new person. If you've written programs in Java, this is mandatory, if I remember correctly, for Java. Now, it doesn't work in this case. And it says you can't convert from a person object to a person pointer, or a person pointer to a person. This new, if we remember, new returns a memory address, and it's going to get stored in whatever is on the left hand side of this equation. It's going to get stored in me. So currently me is an object. It's not a pointer to an object. So we can make it a pointer to an object, and this error will go away. And now if I intentionally made these member variables public. So, and I think actually the use of the parentheses is the parentheses is not standard use in C++. Usually we just write it like this if we're calling the default constructor, the built-in default constructor in C++ that's not written here. So if we try to say me dot first name, something neat just happened then. I typed me dot, and let's go ahead and assign this a value. So if I say me dot, and I hit, let's just double click this. So double click, it converted this to an arrow, dash with a greater than symbol. If I insist on making it a dot, and I attempt to print the name Seth here, me, it says expression must have a class type. It must be an object of this class, but it has type pointer to an object, a person object. So there's an interesting thing going on here that has to do with operator precedence. I think if you, I forget exactly how it works, but the dot operator has either higher or lower precedence than the dereferencing operator. The dot operator is called the member access operator, and this is dereferencing operator. And you can, let me just say that for pointers to objects, it is necessary to, it's more commonly the case that we don't use the dot operator because for reasons that I'll avoid. And what we do is we use the arrow operator. This is called the arrow operator, and it must be used for pointers to objects. So if I want to print my first and last name, this is the way to do it if I have declared me to be a pointer to an object. And it's a good question. Why would we do this? Why wouldn't we just say person me and then say me dot first name and me dot last name? One reason is we have some additional freedom whenever we use dynamic memory allocation. We're not restricted to the amount of memory that's on the stack in a C++ program. And we can generate, I don't remember if I've done this yet, but we can generate stack overflow. We can overflow the stack, exceed the amount of memory that this program is allocated by the operating system by doing something like this, declaring an array of 1 billion elements. I think that'll trigger it. So it failed, the compilation failed, and it says total size of array must not exceed 0.7 FFFF bytes, which is it's difficult to read this value, of course, but 7, 1, 2, 3, 4, 5, 6, 7, 8 probably, or maybe it was 2. the stack size maximum is 2 gigabytes, or yeah, I think that's not a, I don't know. The details aren't extremely important here. The total size. This is called. This is a very. It's a variation of Stack Overflow, and in certain cases we might want to use the new operator because the amount of space. This gives us additional space. Okay. This is an alternative way to do this. This is static. I like this is static. We're not using the new operator. So this is another way of creating a pointer to an object. And if we want to, but still, even if we don't use the new operator, if we want to print the member variables of pointer to you, that is first name and last name, we would have to use this arrow operator, the member access operator arrow as its full name. These two lines of code print the same thing. Okay. But I've just gone into a little bit of, I've given an alternative example to what I'm doing here, but I'm going to use this animal, dog, and cat class a fair bit here. And in the next 20 or 30 minutes. So let me copy the class definitions, and I'll keep person alive, so to speak. Okay, so class animal. And we're going to get into a bit of polymorphism and overriding this eat function. Overriding. So a dog is a type of animal. So that's what the colon means. That is inheritance again. And the dog could have some attributes like a bushy tail and so forth. But for the sake of this content, I'm just going to make the class definitions only consist of a function, a single member function called eat. So cat is also a type of animal, and cat also eats. It eats cat food. A dog eats dog food, and an animal eats something, some generic food. Okay, so we can create animal and dog objects, and we can create them dynamically. We could say cat, some cat, and there is no constructor definition here, so I'm just gonna leave that empty, and we could say, we could create it, we could say pointer to, let's just say a cat star, a pointer to a cat object is equal to new cat and some cat dot eat, or rather arrow eat. Okay, eating cat food, that makes sense. We could do the same thing with a dog and an animal. But we will see that polymorphism is at play here. Polymorphism, poly means many, morph means shape. So the eat function can take on multiple shapes, so to speak. It can perform, it is different. Its output is different depending upon the object upon which it gets called. If it's called on a cat object, it's the cat eats cat food. If it's called on a dog object, it's eating dog food. If it's called on an animal object, which is the parent, some animal, which could be a cat, but we are not specifying. So when some animal eats, and I'm very much in the habit of typing dot instead of arrow because I just use the auto completion, and occasionally I might make a mistake there. So when some animal eats, it eats something. Whenever a cat eats, it eats cat food. Okay, so that is, again, polymorphism. This function is associated, as you can see with the tooltip, with the cat class, because some cat is a cat object. Some animal could be a cat, but by default, this is associated with the animal. This eat function is if we right click and we say peek at the definition, it goes to the definition of eat within the animal class. Polymorphism. Again, a cornerstone of object-oriented programming, along with inheritance. So inheritance and polymorphism and encapsulation, these are all big words that a person should know when talking about when using object-oriented programming. These are tools that are available to people who write in object-oriented programming languages like C++ and Java and Python and JavaScript and others, Ruby, etc., etc. I think Rust, the new popular language, also uses it. Okay, so something interesting happens if we do this. If we define an external function, which you could imagine wanting to do in certain circumstances. By external function, I mean it is not defined within one of these classes, animal, dog, or cat. Rather, it is, and it's also not defined within main because maybe we would like, it's not defined within main. So if we pass in an animal object, we don't pass in, maybe we don't want to pass in a pointer to a dog object here. And this is the first instance of us passing in a pointer, which is kind of tricky. We're not returning a pointer or passing by reference like this. We're passing in a pointer. And we want to make this eat function, call eat function work for animals, cats, and dogs. So maybe we say animal star A, and we call A arrow eat. And again, A is a pointer to an animal object. So when I hit tab there, the auto completion, it makes the member access arrow operator, not the dot operator, not the member access operator. So I'm going to create some animal and some cat and some dog using dynamic memory allocation. And I'm going to say instead of course, this is a fine way to call the eat function, but suppose for some reason that and again, we could imagine some reasons, call eat function. It's all programming design, software design question, whether or not we want to write this function externally like this. Call eat function, and what is the expected type? It is a pointer to an animal object. Okay, so let's pass in some animal, which is a pointer to an animal object. And when we run this program, we get the expected output, eating something. But something interesting happens whenever we say call eat function on some cat or some dog, and that is a legal thing to do. This is legal. And it's a little bit surprising. The argument type is a pointer to an animal object, but a cat is also an animal. So this is actually a legal thing to do. And similarly, we can call eat function on a pointer to a dog object because a dog is an animal. Again, this is related to the word polymorphism. Many shapes. The function takes on can take on many shapes depending on the object which is passed to it. But we're going to see interesting output in these two cases, the lines 84 and 85. We see eating something, eating something, eating something. So it was not determined that this is, I mean, we can see it's a cat pointer to a cat object here, but the call eat function, it's associating the eat function with the animal class. So maybe, is there a way to get around this? And there is. Is there a way to make, when we pass in the dog object, we want to see eating dog food and eating cat food? And it relates to virtual functions. So virtual in C++, this is a direct quote from the guy who invented C++. Virtual means can be overridden. He mentions this in one of his textbooks. Virtual means can be overridden. So this eat function can be overridden by children, classes of the animal class. Function overriding occurs whenever you have a class hierarchy where inheritance is used. So, and that is the case here. Overriding, not overloading. Overloading occurs, if this is one overload of the main function, and if you take an integer and two integers, you've overloaded. If you have int main taking 0 arguments and maybe returning a double, that's one flavor of the main function. This flavor of the main function returns an integer and it takes 2 integers. So that's called overloading. Overriding occurs whenever a child class writes a different definition of a function than its parent class. So eating cat food is different than eating something. Eating cat food is eating something, but it's, let's not quibble about details or get into semantics too much. So if we say virtual, what do we see different output here? And where do we put the word virtual? We put it in front of the word void here. If we try to put virtual here, I think this generates an error. Let's see. I actually can't remember. No, it doesn't. Okay. And it produces eating cat food, eating dog food. I think the standard position, it's a modifier. So we can't, it's a modifier for a function, so we can't put it there. We can't, we've seen briefly, I've talked briefly about how the keyword const can be put right here, and it often is. And it can also be put for arguments. We can specify the arguments aren't going to change, and we can put it here as well. So it's quite the noodle. But I think virtual is not allowed in this position. Yeah. After the parentheses is certainly not allowed inside the argument either, because we're describing a function, not the arguments. Okay, so usually we see it here, virtual. We see this modifier positioned in front of the return type. So if we use this, if we say animals eat function can be overridden, then whenever we call this eat function, this is potentially going to be overridden. And you can see if we hover now, we see inline virtual void. Inline means the function was defined in the same place it was declared. Virtual means it can be overridden by any children of the animal class, such as cat and dog. And we see the expected output there. So virtual, you may need to use the keyword virtual, and you will absolutely see it if you work with class inheritance classes, multiple classes that use inheritance. Okay, we can definitely see some examples in the standard library if we poke into it. Let's go to vector, I reckon. I mean, almost certainly. Virtual, interestingly, it's not found here. Maybe in tuple. Let's go to something that I know has inheritance, which is IOStream or OStream. There's virtual. Okay, so basic output stream inherits from. Now this is a virtual class, so that's interesting. But there's an instance in the term virtual. Okay. So optional but encouraged modification using the override keyword. And let's look at an example of that. Void eat, and I think the standard position for the keyword is here, override. It's a keyword. As you can see, it was popping up in the auto completion in Visual Studio right there. It's a keyword. Many keywords in C++. Perhaps too many. Override. So this is now what does it say if we look this up on CPP reference? Override specifier implemented since C++ 2011. If used, it appears immediately after the declarator. So the declarator, the virtual specifier, and then, okay, go ahead and do a bit more detail than I wanted in the syntax. Okay, let's see. What's the point here? There's also this word final. So, okay, override ensures that the function is virtual and is overriding a virtual function from a base class, a parent class. Okay. The program is ill-formed if this is not true. A compiler time error is generated. So what is this talking about? If I accidentally misspell this function here, it says member function declared with override does not override a base class member. So the function it is not in the parent class, and it's not a virtual function in the parent class. So this is related to something called, and let's look this up. Design by contract, software design by contract. Okay, contract programming. Okay, software design. So not sure if I'm gonna find exactly what I'm looking for here, but the use of interfaces. Interfaces are, I believe, a keyword in the Java language, and we're getting at something called abstract classes as well. So if we use this keyword override, it and let's hold off on what I'm talking about until we get to abstract classes, which will be here shortly. We see a syntax error if we use the keyword override. It can be a good idea to use this. Let's just leave it at that. It's more typing, but there are good reasons to use it. I think it's mandatory in Java in certain instances. So it's good to be aware of. Okay. I didn't include it for the cat class just to demonstrate that it's not strictly necessary. So there's a thing called a pure virtual function, and I put that in quotes. And declaring a function as a pure virtual, making a function pure means setting it equal to 0, which is something that doesn't it doesn't particularly make sense. I mean, what does this do? Do we have to have a semicolon at the end here? Yes, I think we do. Okay, excuse me. No, we don't. Oh, sorry. Okay, this is a pure virtual function and it has no definition, right? So now animal, so the syntax, again, it doesn't make a great deal of sense to me. This is not our typical syntax for a function definition. But we've done something to the animal class now. We have made the animal class abstract. And what does it mean to be abstract? We know what things like abstract art are, and that's we have a vague idea of what this word means, abstract art. We have a vague understanding of what it means to be abstract, stuff like this. Jackson Pollock. What does the word abstract mean? We know it's the antonym of the word concrete, existing in thought, but not having a physical existence or concrete existence. So that's a pretty good definition that helps us understand what it means to make this animal class abstract. This is how you make it abstract. You include at least one pure virtual function in the class definition. And now we see an error. Object of abstract class type animal is not allowed. So animal : eat is a pure virtual function. It used to be just a virtual function here. Now it is a pure virtual function. So if I go back, now we can make an animal object or a pointer to an animal object, and now we cannot, because this is what it means to be a pure virtual function. If you remove the virtual here, I think this is no longer considered Equal only allowed on virtual functions. Equal 0 only allowed on virtual functions. Okay, so what is the point of this? It seems a bit useless to make a class and not be able to instantiate the class, and that's a way of saying what this is. Making an object of a class is often called making an instance of the class, instantiation. Okay, so it's illegal. But yeah, what's the point of making a class if we can't make objects of the class? Well, in certain, this is related to interfaces in Java, and if you think about it a little bit philosophically, um, should we just make a generic animal class? Because there's no such thing as a generic animal, in a way. But so maybe we just want to design this thing, which we could call an abstract data type, an ADT, and we want to specify that children of that types of animals, special types of animals, such as dogs and cats and hominids or whatnot, they must implement certain methods in order to be considered animals. So an animal must eat. An animal must do certain other things like breathing, I suppose. So this is again related to design by contract, abstract data types. And if you make a class abstract by making a pure virtual function, by defining at least one pure virtual function, then in order to be concrete, this class must override the eat function. So if I remove this eat function definition, if I comment it out, then all of a sudden I can no longer make a dog object. So dog is also abstract because the animal eat function, its parent, animal, is the parent of dog, and its eat function has no overrider because I just commented it out. So dog is now also abstract, so it prevents us, the compiler prevents us from making objects of the dog class. Okay, so yeah, I go into some detail here. Just to show this, there is a little bit of overhead associated with virtual functions, and people who write who do a lot of programming talk about this. Size of animal. What is the size of animal at the moment? Size of animal is 8 bytes. And if we remove that virtual modifier and also the backslash, the equals 0. So the size was 8 previously, 8 bytes. And now we have other problems. So let's just trying to demonstrate the point that the size of animal changes, becomes larger if you use virtual functions. If you use the virtual modifier. Just a small point, and it's been a while since I've done this, so we'll actually see if this works in the way I expect it to. Okay, so we have to define the eat function. The semicolon. So it was previously 8, and now it's 1. So that's it's quite the diminishment in size. I'm kind of surprised by that result. I expected a function to I'm kind of surprised by that result, but anyways, it's just a thing that you might be aware of. They can be convenient or useful, but they have some overhead, according based on what we just saw, which was only one example. So you should look into this on your own if you're interested. There's a thing called a virtual table, so we won't get into detail on that. But if you, it's fairly likely you'll see this word again. Okay, we'll get into destructors next time in the next video, but that's it for now.